we're going to prove that differentiability implies continuity. So here's what we mean. Differentiability implies or leads to continuity. So what do we mean? Well, we mean that if we know that a function is differentiable at some point or on some interval, then the function is also continuous on that interval. Okay, so let me grab a straight edge here. I had one. So let me give you just a picture of what's going on, and then I'll walk you through the proof. What we're saying is that if we have a function, we'll call it f, so f of x, if f prime at some value c exists, then f is continuous at c. Another way of saying that is if f prime of c exists, then the limit as x approaches c of f of x is equal to the function value. So if we want to know if a function is continuous, what we do is we can check differentiability, and if we can differentiate it, then it's also continuous at that point. Okay. Some things where what continuous or what continuity looks like again, it's if we have a break, then that is discontinuous, or if we have some kind of jump in the graph like this, that's also discontinuous. So that's what we're talking about for continuity. So if we know that this guy holds, then we're not at either of these two types of items. Now it doesn't work the other way. Just because a function is continuous doesn't mean it's differentiable. For example, we could have a function like the absolute value. Okay, so here's the absolute value function. It's not a perfect drawing of it, but there it is. And this function right here is continuous everywhere. However, it is not differentiable at 0 when x is 0. Okay, so that's the idea. If we know a function is differentiable, then it's also continuous. So let me prove it to you. I'll do my best in explaining why things are the way they are here. Okay, so when you do a proof, you start out with what you know and then what you want to show. So we know that that if a function is differentiable, okay, so we know that our function, let's call our function f of x. We know that f of x is differentiable. Okay, so that means that right there in symbols means that we have some situation where if we take the limit as delta x goes to 0 of f at, let's say, some point, okay, I'm going to call it c, so c plus delta x minus f at c all over delta x, that's equal to, we call that f prime at c. So let me draw a picture of what's going on here, because that's a lot of variables to be thrown at you. So what we're saying is, let's say we've got some kind of function, okay, and we pick some guy on it, we pick some point, we call it c. Of course, if we go up here, we go over to here, then this is the function at c. Now let's go a little bit further over, call it delta x. Okay, so then this guy is at c plus delta x. Okay, and this is f at c plus delta x. And all it says is that right here, if we take these 2 points, if we take this point and push it towards this point, that we can find the slope of the tangent line. That's what this whole mess says right here. Okay? Now, we need to show, from this idea, we need to show that f is continuous at c, meaning we need to show that the limit as x approaches c of f of x is equal to f at c. Here's how we're going to do that. I'm going to make a note here for, I haven't given you this other formula for differentiability, but there's another way that we can look at differentiability. And let me just play around with these variables here and show you it. One way to do it is call this other point something else. Let's call it, I don't know, x. So c plus delta x, we're just going to call it x. So then its height value is f at x. So f at x is equal to f at c plus delta x. Now I'm going to do some replacement. So this is what I got to show. I can't use this, but I'm going to use this guy right here. So now I'm going to do some replacement here. And I'm going to say, okay, the limit of as delta x goes to 0, I'm going to replace this guy in a second too, is equal to, now f at c is the same thing as f at x. So this is f at x. And of course, f at c is still f at c, so minus f at c over delta x. But here's the thing, if x is equal to c plus delta x, then that implies that delta x is equal to x minus c. Basically, I just moved the c over, right? So I get this. So this means that the limit as, now watch what happens. As delta x goes to 0, it's true that x gets close to c. Look, as delta x becomes really small, this guy right here goes to this guy right here, right? They get closer and closer together, so x goes to c. So now watch. I can replace delta x going to 0 with x going to c, because they mean the same exact thing. As delta x goes to 0, that is the same thing as x going to c. And so I've got f at x minus f at c over, and delta x we know is equal to x minus c. So this is called an alternative form of the derivative. Okay, now we're going to use this alternative form. Watch how I'm going to do this. I'm going to start, this is my actual proof. So start with the following. Start with the limit as x approaches c of f of x minus f of c. Okay. Now geometrically, this is really delta y, and this is delta x going to 0. Okay. So again, this is really just delta y. Now, I'm going to do the following. I'm going to go like this. Limit as x approaches c. Now, why I picked this will be obvious at the end. Okay. It's kind of like when people, I'm guessing when they first did this proof, they probably worked their way backward and were like, oh, well, okay, we can get to where we want to go to if we start here. So the limit as x approaches c of the following, I'm going to say f of x minus f of c over x minus c times x minus c. Now I can do that because x minus c is not 0, so I can multiply top and bottom by it. Right? Because x is going towards c, but it's not actually equal to c. So if x was equal to c, now it'd be divided by 0, and I have an issue. Okay, so this isn't a problem here. So this implies this, which implies that the limit as x approaches c of f of x minus f of c over x minus c, that this guy is equal, this guy is equivalent to the following. And what I'm using right here is our product rule for limits. But this guy right here okay, is equal to, where it's equivalent to, f prime at c times, now look at this, as x approaches c of x minus c, this guy, x goes to c, so this will become c minus c, which is 0. So this guy is 0, this guy is f prime at c, which is 0. So here's what I've discovered from this whole thing. The limit as x approaches c of f of x minus f of c is 0. Because I started with this guy right here, and I worked it down so that it was equal to, I showed that it was equal to 0. And now watch. I'm going to take the limit because I got minus in between here, so I'm going to bring it in. Oops. So that's true. And the limit, this f of c is just a value, so it's a constant. So this is a constant number, and it's actually equal to f at c. Think about this as if it was like the number 10. As x approaches c of the number 10, it's still 10. Okay, so this gives us the limit as x approaches c of f of x minus f of c is 0, and then the limit as x approaches c of f of x then must be equal to f at c, which this, guys, is the definition of continuity. Okay, so what we've done is we started out, and this is how proofs work, we started out with what we know, and we showed that from this it must be logically true that this guy also is true, right? So this implies this. Now you can't go the other way, okay? Just because something's different, or just because something's continuous does not mean it's differentiable, and I showed you an example of that.